Okay, so welcome back. So we have Viraj, who is going to tell us about Sapphire.
All right, thank you so much. Great to be back in Santa Cruz. I'm excited to tell you about some work that I've been doing over the past few years to try to enable interpretable precision astrophysics for galaxy formation. So it was 4 years ago, almost to the day, where I finished my PhD here at Santa Cruz with an amazing set of mentors shown here. In retrospect, I realized that the problem that I chose was borderline intractable. And I think it's still borderline intractable. The idea is to emulate hydrosimulations of galaxy formation using simple but still physics-informed and interpretable models. 4 years ago, I didn't know that we were on the cusp of this AI revolution, this idea that you can optimize the values of billions of parameters for things like ChatGPT. So since I left Santa Cruz, what I've been trying to do is to adapt some of that AI technology, not for black box machine learning, but to improve the way that we develop our models and accelerate the way that we calibrate them. So the two pieces of key technologies that enabled the AI recently are GPUs, which enable massively parallel computation. Many people here already use GPUs for galaxy formation simulation, so this is not that new to this crowd, I think. But something else that we don't talk about too much, I think, is automatic differentiation, which I describe as the third computer science way of taking derivatives. It is not taking derivatives by hand, which is not possible in our numerical galaxy formation models, and it is not finite differencing-based derivatives, which are very expensive and very numerical error prone. So we'll come back to both of these things later in the talk. The other thing that I'm very excited about is this big data revolution, where these upcoming missions are going to map in ever greater precision things like the cosmic microwave background, large-scale galaxy clustering, the manifolds that are relatively thin that are occupied by observed galaxies. This is one of the things that tells many of us that even though individual galaxies are very complex, as a population, there have to be some deep physical laws that guide them towards these equilibrium attractor solutions. And then similarly, these morphological sequences, which also reveal that there's some kind of regular patterns in the galaxy population. So I'm going to argue in this talk that we don't actually have the models or the methods to take advantage of all of this forthcoming big data, which is a shame because we really want to try to use galaxies observed with these surveys to test our standard cosmological paradigm, which, as we learned early this week, Sandy, Joel, George, Avishai, and others played a big role in establishing, in which the evolution of galaxies and the universe is degenerate, and it's dictated by three things that we don't really understand: inflation, dark energy, dark matter. Of course, this paradigm has been great because it's become the backbone for these many cosmological simulations that many different groups have been able to run. And these are great because they make detailed predictions for various galaxy properties. About 10 years ago, there was a nice review article by Rachel Somerville and Romeo Devey, which showed that these different galaxy formation simulations make predictions for galaxy scaling relations that you can compare to observed ones. So things like ISM gas fractions versus stellar mass, and then stellar mass metallicity relations. And in some cases, the simulations agree with each other. In other cases, they don't. It's not always clear what it even means to get this right. And part of the reason, as we all know, is that the physical processes involved in galaxy formation, first of all, we don't understand many of them from first principles, but they're also non-linearly coupled across an enormous range of scales. And because we can't actually observe individual galaxies evolving, we don't have a choice. We have to resort to statistical modeling approaches. We have to try to do parameter variations to even have a hope of saying something about causality, and we have to provide uncertainties on the predictions of our models. This is very challenging. There's the camel suite that we're familiar with that Daisuke mentioned yesterday. Phil Hopkins, I think Sergio later in this session is going to talk about parameter variations as well, or physics variations. These are great. They're great for people like me and many of us in this room. They're like a sets of priors for our galaxy formation models. But of course, these are numerical experiments, right? They're not a replacement for theory and understanding on their own. So the only real game in town for the past 15 years or so to try to do these robust statistical models connecting observed galaxy populations to our dark matter simulations are what are called these empirical modeling approaches that you heard about in Aldo Rodriguez Pueblo's talk, Haowen Zhang's talk, Risa Wexler's talk, and others. Although I would argue that basically every galaxy scale model that we currently have, they're all empirical, right? Because choices are made for numerics, for physics, and so on. Imagine you had a framework that could give you the best of both worlds. A dynamical model that could reproduce the observed evolution of galaxy populations as a function of time, and also respect and inform the emergent predictions from these kinds of very complicated, sophisticated numerical simulations. So over the past few years, I've been working with my amazing team of colleagues here to develop such a model that we're calling Sapphire. It doesn't stand for anything. And the basic question that I'm interested in answering for now at a high level is, how do galaxies exchange mass, metals, and energy with their surrounding gaseous atmospheres and their surrounding cosmic ecosystems? So this is a dynamical model. For now, it's a two-zone model. There's a central galaxy and there's a surrounding gaseous atmosphere. Both the central galaxy and its atmosphere have sets of state variables, not unlike orbital dynamics or thermodynamics, but here we have galactic scale state variables. And then we want to track the coevolution of those state variables as a function of time, accounting for various processes that involve flows of mass, metals, and energy. So I keep saying dynamical model. What does that mean? It just means that in this model, the state variables co-evolve according to a system of non-linearly coupled ordinary differential equations. So I don't have a lot of time to walk you through the details of this model, but essentially I like to think of these as galactic scale continuity equations for mass, metal mass, and the new thing that we added here was keeping track of the thermal energy and turbulent kinetic energy of this CGM zone. Every single term here on the right-hand side represents an individual physical process, and it has to be parameterized in some way. And I'm actually amazed that you go back 50, 60 years to papers like Beatrice Tinsley, 1968, and they postulated functional forms for some of these parameters that actually now agree pretty well with our best, latest simulations. So what I did is I went into the fire simulations to provide one set of priors. I'm agnostic, but one set of priors for how do I parameterize the many parameters, the inputs to my model. There's about 20 free parameters that encode the ignorance that we have about star formation, stellar feedback, CGM structure, turbulence, driving, dissipation, and so on. Right? So I actually went into the simulations, I measured these, and I fit functional forms, did the best I could. And there are interesting, systematic trends here with redshift and halo virial velocity and so on. And then I took that model with that set of priors essentially for functional forms for those parameters. I ran that dynamical model on the merger trees of the individual fire galaxies, and my colleagues and I were amazed that we got even within a factor of 2 of the time series evolution, the time evolution of things like the masses of the different zones measured in the simulations and predicted by the dynamical model, which is very simple. The turbulent kinetic energy versus thermal energy partitioning of the CGM as a function of time, the total halo baryon fractions, and then this is a dynamical model also, it's achieving this agreement in essentially the same way as what's happening in the simulations by reproducing the flow rates of mass, metals, and energy as a function of time for individual galaxies spanning a range of halo masses and redshifts. And you can play this game, you can go to other simulations. So with my student Yossi Cohen, we've been going and analyzing the TNG simulations to extract similar kinds of functional forms, which tend to be different from what we find in fire. So another set of priors. But I want to switch now to something else. So my goal here is I'm agnostic about the simulation, the dynamical model. I ultimately want to try to discover the space of plausible dynamical models for galaxy population evolution from the data. It's going to be a long road to get there, but to take a first step towards that, I've rewritten Sapphire in one of these lightweight machine learning packages known as JAX. And JAX gives you a couple different things. One of the first things it gives you is the ability to run your code on multiple CPUs and GPUs in parallel. And so I mentioned I have these 8 coupled ODEs for one Galaxy CGM system, but if I want to do inference, if I want to do parameter variations for causality experiments, I need to run possibly millions of these things, right? So amazingly, I can't get into this in too much detail, but we're now in a regime where the models are fast enough that you can do on-the-fly inference. You don't need an emulator. at least with this baseline model. So for example, I can do thousands of halos in parallel in a few seconds, and typically you need much fewer halos than that for on-the-fly inference that I'll show later in the talk. So you can do it in a fraction of a second in parallel. So now you're really in the same regime like some of the empirical models. And when you have more than 1,000 halos, you can run on multiple GPUs to generate training data and so on and so forth. But the new thing I want to talk about is there's a fundamentally different way of assessing the sensitivity of our galaxy formation models to our uncertain astrophysics assumptions. Instead of just doing these coarse parameter variations, what you can try to do is compute the gradients of the model. I'm not talking about color gradients or radial gradients, even though I love those things. I'm talking about parameter sensitivity gradients. So this is a Jacobian matrix for one Milky Way model galaxy at redshift 0. And 1 point in parameter space. So these different columns show you the parameter sensitivities as I tweak each of these individual parameters, and then the rows are the different state variables. So you notice here that there's one column that is really like lit up. This is the energy loading factor of supernova feedback, and we'll come back to this later. So one thing, when I first computed this and I saw that it has non-random structure, I immediately asked myself, well, is this actually astrophysics or is this numerical garbage? And there's many ways to test that, and one of the ways is, well, you can still do your by-hand parameter variation. So with Chris Carr a few years ago, we used a simple version of this model to vary the mass loading and the energy loading parameters of the model, and we showed that in the framework of this particular model, the stellar to halo mass relation is not sensitive to mass loading variations, but it's very sensitive to variations in the energy loading. So this confirms, you can just look at the relevant cells here, stellar mass gradient with respect to mass loading and energy loading, and you can see that there's like basically very little sensitivity for mass loading, but this thing dominates for energy loading. That was for a single Milky Way model galaxy at 1 point in parameter space. Naturally, the next thing you would ask is, well, what happens if you look at a variety of mass accretion histories or different parts of parameter space? And so that's what this shows. This is only possible when you can run this on multiple GPUs, because it's still very expensive. And so what this shows is across parameter space for these 9 different parameters, and across for many different halo mass accretion histories that I got from n-body simulations on which I run this model, energy loading is king. These are the norms of those Jacobian parameter sensitivity columns divided by the norm of the entire Jacobian matrix over millions of halos, over millions of parts of parameter space, and energy loading is king. There's other interesting features here that I can't get into, but we can talk about that. One other thing I want to just talk about with this is you can also compute second order gradients. So you can compute something called a Hessian matrix, which is related to something that you may have heard of, the Fisher information matrix that is routinely used in cosmology. So we always say we want to try to do precision cosmology, which for me means I want to make corner plots for galaxy formation. Right? And so we can actually do that now. This has only really been the domain of empirical models now, but we can do it with dynamical models. Right? So what this is showing is just for 4 parameters, you have these little Fisher contours, and the orientation, the size, and the shape of these Fisher contours is different in different parts of parameter space. And so if the real universe lived in some particular part of this parameter space, the sensitivity of things like the stellar to halo mass relation to the astrophysical parameters is going to vary depending on where in parameter space you are. Okay, so you can spend an entire career studying the properties of those matrices, but I want to switch and end with something practical, which is gradient-based inference. So one thing that I've been interested in over the past few years is that different simulations predict different mass, energy, and metal loading factors for supernova feedback. And I want to know, can we infer this from data using this new dynamical model? Because then it can kind of constrain these simulations, kind of like how we currently benchmark our simulations against the stellar to halo mass relation that we get from empirical models. I want to try to provide constraints from these kinds of models on new simulations, that you should not exceed energy loading of this, of this magnitude for galaxies of this mass and so on. So what I'm going to do is I'm going to assume that mass, energy, and metal loading, as well as the ISM depletion time, fall off as power laws as a function of V-veer, or halo mass. I'm going to fix the other parameters to the priors that I got from the fire simulations for now. And so these are some draws from a uniform prior for these power laws of eta E as an example. And then I'm going to use 3 sets of constraints. I'm going to use stellar to halo mass relation at redshift 0, ISM gas fractions, and I'm going to use the stellar mass metal density relation despite its large error bars. And so these are just prior predictive checks. So you can take draws from your prior for your parameters, and you can see that our model is spanning the range of the data, so we can try to fit it. And I'm going to assume, in this case, a very simple Gaussian likelihood with no covariances, just to get things moving. So skipping, focusing really quickly on mock tests. So generally, when you want to do inference, you have to do mock tests. It's very easy to apply this model directly to observations, and you get some posteriors out, but you can't interpret them unless you do mock tests. And you can't do mock tests with these kinds of models unless you have gradients and you can run them very quickly. And now we can do that. So this is precision on the left. This is if you use only the stellar to halo mass relation or combined it with ISM gas fractions or added mass velocity information, what is the precision that we get? Don't worry about, is the model wrong or right? This is just precision, right? And so we can get percent level precision if we ignore measurement errors. Accuracy, we're very accurate generally with these mock tests. We're within 1 sigma of the true minimum generally, so we're not biased. Now applying it to the data. So this is applied to the three redshift 0 scaling relations together, or quasi-observables, whatever you want to call them. There's 2 sets of contours on here. One is the Fisher contours at the maximum a posteriori estimate from gradient descent, which finishes within a few seconds. And then something else is fully Bayesian inference from Hamiltonian Monte Carlo, which I can explain to you later if you're interested, and that's in blue. And they're amazingly consistent. So first of all, let me just show the prediction, the posterior predictive checks from the model actually agree with the data, so we can actually interpret the parameters. And what the parameters imply here is just that the mass loading has to be low. And this is in contrast to what is typically assumed in large volume simulations, which require large amounts of gas to be ejected. But it's consistent with small-scale simulations and many observational results, including what we heard yesterday from, I forgot the name of the person. But energy loading has to be high. Metal loading is unconstrained currently because the error bars on the observations I've used are pretty large. So this is essentially a path towards precision astrophysics. There's a lot more I can talk about. I'm not going to talk about it. I've been working with an amazing team of people to study or flesh out a lot of the missing details in Sapphire, black hole feedback, different inference techniques, synthetic observations, CGM, and then the next talk, my student Austin Gabriel Pillai is going to mention what he's doing with putting in satellites and subhalos into this framework. Okay, I'm out of time, so I'm going to end with my takeaways and hope to talk to you later.
Thanks, Viraj. We'll take maybe one question.
This is fantastic work. But there's an issue. Suppose I would go to an actual hydro simulation, pick whatever your favorite is, bio or whatever, and you go and look at a Milky Way halo, and you can, in principle, in the simulation, actually measure what the energy feedback parameter is, and eta. And I'm pretty sure if I would do that and evolve it over time, and then V-veer is changing, I'm sure it's not going to follow a nice power law, and so there's a lot of stochasticity to that parameter.
Yes.
And so, have you considered including that? So in other words, you can't it's not described by a single parameter. Mm-hmm. It's a parameter that probably has a huge variation. How does one deal with that, and how important is it?
Hierarchical Bayesian modeling. So this is where I've assumed a very simple deterministic mapping between V-veer, redshift, and the eta E, eta M, and so on. But there's no, I don't believe that. Myself, I don't believe it. So I want to try to discover how should I parameterize it. And are there other dependencies? And there's principal ways of doing this within a Bayesian framework. So hierarchical modeling is one way.
Can the next speaker set up? We'll take one question.
Viraj. I have a question about energy loading. What does it mean? I mean, it's like a fuzzy word.
Yeah, sorry, I had to cut that slide. Energy loading is analogous to mass loading. So mass loading is defined as the mass in the outflow in the galactic wind divided by the star formation rate.
Yeah, I
Energy
understand.
loading is the energy carried by that galactic wind divided by the 10 to the 51 ergs supernova energy per 100 solar masses of stars formed times the star formation rate.
But how could that happen? Energy is conserved.
What do you? I mean, the energy is conserved for the entire two-zone system, but not from the ISM alone. Energy can escape, mass can escape, but the entire system, we maintain continuity. So I don't understand the question.
So the amount of energy escaping, could that be larger than what's generated by supernovae?
No, I impose energy loading is capped at 1.
So the parameter is less than 1.
Yeah,
I see. Okay.
yeah.
Okay, let's thank Viraj once again and